Thank you, question, and thank you again for every author contributing to this variation issue. And it is very exciting. So I'll just make it brief that we all see the value that the society needs credible and usable forecast at the S2S, the subseasonal time scale. That's mainly because that extreme events often result from small-scale weather phenomena, but can also be associated with persistent and larger-scale climate patterns, something like El Nino teleconnection or NAO, or simply frosty waves embedded in a jet stream. We also probably know that the dilemma we face right now, that the larger-scale models, which can depict this persistent pattern, cannot resolve mesoscale phenomena. And mesoscale models are regionally confined and then cannot really depict larger-scale climate variability. The seamless approach of running them both together with high-resolution multi-time scale models that currently they don't really provide a good future for the skill for the forecast yet. So Kathy and I feel that what needs to happen to address this problem for the time being is for the mesoscale weather and larger scale climate communities to come together and define the best approaches to a solution. And we are lucky to have all the presenting authors today contributing to the variations to address this problem. So with that, I'll leave it back to you, Kristen.
Great, thanks, Simon. So I'd like to introduce all 5 of our speakers. They're going to go back to back, so we won't have introductions in between. First up is Chris Castro from the University of Arizona. Following him will be Paul Ullrich from the University of California, Davis. Ruby Leung from the Pacific Northwest National Laboratory. Emily Becker will follow her. She's from the NOAA Climate Prediction Center. And we'll wrap up our webinar today with Trent Ford from the Southern Illinois University. With that, I'd like to hand it over to Chris. Go ahead.
Okay, thank you very much. So today I'm going to be talking about a new paradigm of convective-permitting modeling and S2S forecasting of warm season precipitation extremes. And what you see on the cover slide is an example of extreme events that are important to Arizona, so monsoon thunderstorms associated with outflow boundaries and microbursts and dust storms. So the need for improved S2S forecasts is really motivated by the issue of socioeconomic value. That billion-dollar disaster events during the warm season we know are becoming more extreme. These include heat waves, drought, wildfire, and flooding. So there was a recent report issued entitled Next Generation Earth System Prediction Strategy for Subseasonal-to-Seasonal Forecasts. It's a Review National Academies report that was recently published. And if you see one of the seminal figures from the first chapter, this gives the relative importance of S2S prediction for various sectors in relation to timescale. So notice that the S2S timescale, we have key areas such as agriculture, water resources, emergency management, and energy. So a goal that this report sets is that S2S forecasts should be reliable as weather forecasts are today. That's almost a direct quote from the opening chapter of the Academy's report. So if we're, say, from the issue of climate change, this is a motivating issue of why we need greater predictability at the S2S timescales, because we know that climate change is doing 2 things with respect to warm season precipitation extremes. One is because of increases in long-term moisture and instability, this is making the atmosphere more thermodynamically favorable for more intense precipitation. So there have been numerous studies on this point. I show an example from the Min et al. Study that shows the observed increase in change in daily precipitation. And you see that across the United States, that precipitation intensity is increasing, generally if we're considering daily precipitation throughout the whole year. The other issue in the mid-latitudes relates to dynamics, that we are observing more persistent atmospheric blocking. The precise dynamical mechanisms may be debatable, but this is potentially resulting in longer duration extreme events on the S2S timescales. And this is the classic figure from the Francis and Vavris paper. So if we're talking about the warm season, in the mid-latitudes, really thunderstorms are the particular concern. Those include supercells, mesoscale convective systems, and squall line and mountain-based convection. Each one of these has its unique associated severe weather dangers. So supercells have tornadoes, large hail, heavy rain. MCSs, squall lines have straight line winds, flooding. They're a trigger for dust storms if they occur here in Southwest, for example. Mountain convection should not be neglected also as a severe weather hazard, especially here in the western United States. It's a trigger for flash floods, microbursts, as I mentioned in the opening slide, lightning, and the lightning is a trigger for wildfire, and microbursts can help spread wildfire. So we know that if we look at the current scale of NMME forecasts, and this is a figure from a recent BAMS review article by Kurtman et al., this shows the ranked probability skill score of a 6-month precipitation forecast. So at the top row is the winter, at the top and the bottom is the summer. So we know, and it's been known for a long time, that in the cool season, there's relatively good skill in these NMME models for precipitation, and especially in those areas that are influenced by ENSO. So for example, if you look at all the NMME models, they have pretty good skill here in the Southwest. If we look at the summer, there's comparatively much poorer skill in the warm season, so almost all white on the map, or with even some green areas if we're looking at just the CFS version 2 that's indicating negative skill. And so there's two possibilities for this relatively poor skill. One is that the models, the global seasonal forecast models, might be relatively more challenged to represent in a deterministic way atmospheric teleconnections during the warm season. Or another possibility is that the dependence on parameterized convection in these global models results in a relatively poor precipitation forecast. It might be a combination of the two. So going to the first idea of investigating atmospheric teleconnections, the idea here is that warm season teleconnections organize the continental scale patterns of temperature and precipitation anomalies, very similar to how they do in the winter. These modes may be internally or forced or externally forced. Internally means they arise as a result of pure stochastic forcing internal to the atmosphere. Externally forced is they're related to no natural modes of climate variability, for example, MJO or ENSO. So some keys to S2S predictability is we need to know if the dominant warm season teleconnection modes and their forcing mechanisms exist as a salient feature within any global S2S model, and that the modes are deterministically predictable at the continuum of S2S timescales. So in the figure shown here is an example of the two known dominant warm season teleconnection patterns from work by Xinhua Ding, the circumglobal teleconnection and the Western Pacific North America pattern as seen in 200 millibar summer height anomalies. And these patterns, as you see from the text on the figure, are related to phasing with ENSO in its developing and decaying phases with respect to each pattern. So our own work has looked at this too from the perspective of dominant patterns of warm season precipitation, for example, in PRISM data. And what we found is that we basically recover these same dominant patterns in the precipitation signals. And you see the cartoon of the teleconnection patterns presented here, the Western Pacific North America pattern and the circumglobal teleconnection pattern. What we think is very interesting about the WPNA pattern is this seems to have a very strong tie to ENSO and Pacific decadal variability. and therefore we think it's probably the most seasonally predictable. The other modes may have some seasonal predictability as well, but they are certainly for the CGT that we know that that arises as a pure stochastic mode of variability in these global models. If you look at the colors on the figures, the red and the blue, these show the predominant projections of precipitation associated with these modes, and what you can see is that the majority of the colors of the red or blue is focused to the western and central United States. So these are where these modes most strongly project onto the precipitation within the contiguous United States. And so if we're looking for potential predictability, it's principally in the western and central United States. So the other part of the puzzle is the convective-permitting modeling. So we know that atmospheric models at a meso-beta scale resolution, nominally grid spacing on the order of 10 kilometers, with parameterized convection, have a relatively poor representation of warm season precipitation as compared to the cool season. So there is a growing body of literature in this area of convective-permitting modeling, nominally less than 5 kilometers at the meso-gamma scale, and this has been demonstrated to result in the better physical representation of storm scale structures, timing, and propagation. And from the perspective of climate, it yields better statistical characterization of convective precipitation extremes. So here, just to emphasize the point that this is the emerging standard within the National Weather Service in the high-resolution rapid refresh model, you see an illustration, the 12-hour HRRR forecast simulation of an East Coast derecho event that occurred in late June of 2012. And you see that this is very well illustrative of that you're explicitly resolving the convective structures associated with the derecho event. For what we're talking about here, there's presently little to no application of convective-permitting modeling to address the issue of warm season S2S predictability. One solution we suggest that is multi-RCM ensemble downscaling, and this has been done previously for the cool season in the context of the MRED experiment. Multi-RCM ensemble downscaling of multi-GCM seasonal forecast, the so-called Mr. Ed experiment. So this tests the usefulness of downscaling winter seasonal forecasts from global models using an ensemble of regional models. Downscaled 23 years of December to April reforecast from the NOAA CFS, that was at the time version 1 seasonal forecast model. And with over coterminous U.S. domain at 32 kilometers, downscaled each member of a 10-member CFS ensemble for each winter from 1982 to 2004. And this is a figure provided by Ray Arrett at Iowa State, who took the lead on the project subsequent to the death of the original PI, John Rhodes. So this is, you see John's figure at the lower left-hand side. He unfortunately passed away in the middle of the project, and then Ray took over. But this gives you an idea of the strategy of the MRED ensemble, which can be adaptable to the warm season in a convective-permitting modeling paradigm. So you're taking for example, one global S2S model at its various initialization times, and then you're using that for a suite of regional models. In this case, you see approximately 7 regional models with the various initial conditions. So a multi-ensemble, multi-model approach. And this is actually very similar to other community exercises that are doing climate change projection, for example, North American Regional Climate Change Assessment Program. So some lessons that were learned from the MRED project and similar work is that the largest improvements are obtained in regions where the global models already demonstrate some skill, tied largely to the deterministic representation of natural climate variability. And the greatest value added is where is it to be expected where climate modes project strongly on regional precipitation, for example, ENSO, and we already know that from the global model results from the Kurtman et al. Paper I showed earlier. And similar work that we've done with WRF in conjunction with collaboration from NCEP, and I know we have some NCEP participants on the call, basically shown the same conclusion holds for the warm season. So this is an example in the figure of the dominant mode of early warm season precipitation in WRF dynamically downscale CFS version 1 forecast and their corresponding relationship to 500 millibar height sea surface temperature anomalies. So you see this antiphase relationship between the Pacific Northwest and the Southwest and Central U.S. tied to the WPNA pattern tied to ENSO forcing. And you can see, as I said before, greatest areas that are ringing in the pattern are the western and central U.S. So these would be the a priori target areas where we think convective permitting modeling might add the most value at S2S timescales. So we suggest the way forward to address the warm season S2S challenges is the exciting thing is it's now technically feasible to apply convective permitting modeling at S2S timescales, deterministically characterized model forecast skill of extreme precipitation over a long-term historical climatology. And this has only been possible in the last year or two because of the availability of sub-daily reforecast data necessary to force a regional model. So we suggest a robust methodological approach to investigate the warm season S2S problem based on convective permitting modeling would incorporate the use of multiple S2S global forecast models and or ensembles across a continuum of S2S timescales to assess deterministic predictability of warm season atmospheric teleconnections using data from the NNME reforecast, and then use one or more limited area models, for example, WRF, perform dynamical downscaling of global S2S model ensemble data using a convective permitting modeling approach. And this is even bigger than MRED because of the complex regional modeling involved, and you definitely need a coordinated multi-institutional effort to distribute the necessary data analysis and modeling tasks involved. And with that, I will conclude.
Great. Thank you very much, Chris. We have time here for a couple questions if anyone has any. Just a quick reminder, feel free to raise your hand. I'll take you off mute, or you can type them into the chat feature. We do have a question, Chris, wondering if you could address potential computation cost issues.
Well, just to give an idea, there was a recently published paper that I just saw came out yesterday, published by the group in MMM and RAL and NCAR. So they dynamically downscaled just about a decade's worth of ERA interim data at 4 kilometers. That took several years worth of computing time on Yellowstone, on resources at NCAR, generating petabytes worth of data. So we really need to get the national labs involved in an effort like this at a much grander scale, I think, than they were even in the previous MRED effort.
On one of your slides, Ari Gerson has a question. On one of your slides, you charted industry needs for forecasting by timescale. How do you collect this data, and do you think any industries will change if S2S ever became dramatically better?
Well, that's a really good question, and just to comment, that's the first slide, and that's not necessarily work that we have done, but that is the general conclusion of the National Academy's report. I can comment on the work that we individually do in Arizona with our local stakeholder community. Is they have expressed a sincere desire for this S2S type of information. I'll give you an example. In Arizona, a big danger during the monsoon is flash flooding. So if you can have better forecasts of the monsoon and better characterization of the potential for flash floods and associated monsoon precipitation extremes, yes, that has that societal value in planning.
Great, thank you, Chris. If there's any additional questions for Chris, we can take those at the end, and if not, then we'll move on right now to Paul. Paul, are you with us?
Yep. Can you hear me okay?
We can hear you now. Go ahead.
Perfect. All right. Well, good morning, everybody. And today I'm going to be talking to you about an alternative modeling technique. Notably, I'm not really, don't have past experience with the S2S community so much, but am instead approaching this problem more so from the standpoint of kind of climate models being brought down to the scale of forecasting for both short-term as well as investigating the possibility of adapting these climate models to for use on the S2S timescales. So this is work that is underway in my group here at UC Davis, as well as with Colin Zarzicki at the National Center for Atmospheric Research. So as Chris pointed out, I think there's this need that we have for high-resolution modeling. And the rationale behind this need is driven by kind of an improved resolution of land surface processes, in particular snowpack and runoff, as well as a desire for improvements in other parameterized processes or the removal of parameterizations from the modeling system. Also, we want to resolve more transient eddies, including synoptic scale frontal systems and local convective systems, in particular such as the derecho that we saw earlier. We want to have improved resolution of extreme weather events, and we want to have improvements in the representation of geographic features such as mountain ranges and islands. So I'm coming from this from the perspective of kind of a resident of California, and California is notorious for needing high resolution when it comes to both climate and weather modeling, in part because the California coastal ranges have this profound effect on the regional climate and drives kind of the microclimatic system that we see here in California. So we know that we have supercomputers that are effectively increasing in power approximately every 1.2 years. This trend has been fairly consistent since even the early 1990s. One would expect then that as you get basically a if you require basically a factor of 2 horizontal refinement in your modeling system, then in conjunction with the time step drop that you would also require associated with that, you would then require about 8 times the computational power in order to effectively double your resolution. So this suggests that we should expect to be seeing a doubling of horizontal model resolution about every 3.6 years. However, that really hasn't been the case in the climate community. Basically, with the first assessment report from the IPCC in 1990, we had model resolutions of 500 kilometers. 5 years later, we did see a doubling of this resolution among that modeling ensemble. But then another 6 years after that, with the third assessment report, we only saw basically a mild increase. And then it took until about 2007 with the fourth assessment report before we effectively saw another doubling from 1995. With the fifth assessment report in 2013, actually, the model resolution pretty much stuck around at about 1 degree global resolution, or about 110 kilometers. So we haven't been seeing kind of the dramatic improvements in model resolution one would expect. With AR6, it's anticipated that we're going to see some improvements, with some models run at 50 kilometer and perhaps even higher quarter degree resolution for climate timescale. But as Chris mentioned during his talk, I think it's clear that for seasonal, subseasonal to seasonal projection, we need to have even higher resolutions than that. So what is the reason for our failure to really follow this hardware curve when it comes to model performance? Well, one is that it's difficult for the software systems in order to actually leverage the power that the hardware systems provide. But secondary to this, we also know that high-resolution models are typically expensive to run. This implies to some degree that they are hard to tune, and so it's difficult to demonstrate significant improvements in simulation quality as you go to higher resolution. This is generally observed in the fact that even if we go to higher resolutions in our modeling systems, even if we bring our climate models down to a 1/4 degree global resolution, there's often not a significant improvement in the mean climatology. So I think we have to look beyond then improvements in that mean climatology that we would anticipate from improvements in model resolution, and instead look at the other benefits that improvements in model resolution would get us. So in particular, during this talk, I'm going to focus on two aspects of high resolution that we do know are necessarily improved. That includes the resolution of extreme weather events, such as tropical cyclones or atmospheric rivers, as well as the improvement of geographic features. It's well known that much of the improvement that we get from climate modeling systems at higher resolution is brought on basically by improvements in the representation of the underlying topography. So basically, this is our starting point then. We have these global quasi-uniform grids that have become pervasive in the climate modeling community, including the cube sphere grid here on the left and the geodesic grid here on the right. These are designed in order to provide basically quasi-uniform coverage of the sphere at approximately the same model resolution. This has the advantage then of having a consistent time step over the whole grid without the need for instance, polar filtering, which has been used in the past on the latitude-longitude mesh, as well as basically providing this uniform coverage. However, what is coming more and more to the forefront, kind of as an emerging technology in the past several years, is this variable resolution climate modeling technology. Variable resolution models require a bit of software engineering expertise in order to pull off, hence why they haven't really come to the forefront of operational use or scientific use until fairly recently. Variable resolution is known to require basically fewer computational resources to be spent sparingly on a single problem. And we believe that this high resolution then is useful for seasonal to subseasonal forecasting, where you have that two-way flow of information from the high resolution domain to the low resolution domain, and vice versa. Hence, you can do basically long-term simulations, which require resolution of global teleconnections while still getting the high resolution you need in order to capture local weather features. Also, this technology allows us to reduce the overall computational cost of high-resolution simulations if we're only interested in a particular region. And so it allows us to produce basically a large number of ensemble members dealing with a particular region, for instance, as shown here, the western U.S. And again, basically you can target resolution where you need it. So variable resolution models have emerged from a number of operational centers. So we've seen, for instance, the conformal cube sphere mesh emerging from the community Earth system model, as well as the accelerated climate model for energy, both of which are under development at NCAR and the Department of Energy. We have the stretched icosahedral mesh, or geodesic mesh, or centroidal Voronoi mesh, goes by several names. And these are used, for instance, in the model for prediction across scales, which is developed in the atmospheric model is being developed at NCAR, and the oceanic model is being developed at Los Alamos. Also, there's work going on the non-conformal cube sphere mesh, for instance, under development at Lawrence Berkeley National Lab for their Chombo dynamical core, as well as the Neptune model being developed through the Navy. So as we resolve these models to higher and higher resolution, it's quite apparent that we get better resolution of climatological features. Here, for instance, we're showing the improvement in precipitation statistics that we observe from the community Earth system model as you increase the resolution over the high resolution patch covering the western U.S. So at 1 degree resolution, basically we have very poor we very poorly capture kind of the intrinsic features associated with California's kind of unique topography, including, for instance, the Sierra Nevadas, which are responsible for quite a significant amount of total orographically driven precipitation, but it effectively is not present in the uniform 1 degree simulation. As we go to 28 kilometer and 14 kilometer, you get much better resolution of those precipitation statistics locally and a better representation overall of total precipitation. So basically seasonal variability associated with that precipitation. The 3 reference solutions are shown here at the bottom, coming from the North American reanalysis, the UW precipitation data set, and PRISM precipitation. As you can see, the 14-kilometer CESM variable resolution model does a fairly good job of capturing the spatial distribution of precipitation and matching these reference data sets. Atmospheric rivers are, of course, a major driver for extreme precipitation in the West, and one of the targets of S2S prediction. So for our atmospheric river study that we're performing here at UC Davis, we're looking at how well the high-resolution region captures these atmospheric river events and how much upstream area you need to actually cover in order to ensure that those atmospheric rivers are captured with sufficiently high fidelity. Here is one of a snapshot of column-integrated water vapor and total precipitation from one particular atmospheric river episode simulated with the variable resolution CESM. As you can see, it's able to capture some of the coastal influences on the precipitation statistics from this atmospheric river episode. Tropical cyclone climatology with variable resolution is being pursued as well, and this is going to be interesting from an S2S perspective, just in order to get total tropical cyclone statistics in the North Atlantic Basin. What we've seen is that in the variable resolution CESM, with a resolution over the high resolution patch of about 1/4 degree, we actually do a very good job of matching the overall tropical cyclone statistics in the North Atlantic compared to observations. So if you just look here at the tropical cyclone tracks shown in figures B, taken from the variable resolution model, and the observations shown in figure C, you'll notice agreement over the high resolution patch. Whereas this agreement does not carry over in the low resolution regions such as the North Pacific or the Indian. We can also use this technology in order to do forecasting. So this is a study that we're looking at for adapting a climate modeling system in order to apply it directly to weather forecasting. Here, Collins Zarzicki has used the variable resolution CESM at 8-kilometer resolution over the high resolution patch in order to forecast Typhoon Haiyan. And what he observed was that the wind speeds actually matched very closely to observations, as well as capturing much of the fine banded structure that is present in the storm. At this point, since the variable resolution CESM is purely a hydrostatic model, there is some concern to, of course, bringing it down far below 10-kilometer local resolution. However, for orographically driven precipitation, we have brought it down to about 3.5-kilometer without significant issues. It's also been used for forecasting Hurricane Sandy. Here you see three initializations for variable resolution, high resolution everywhere, and low resolution everywhere on the far right-hand side. And these simulations were run forward for a 120-hour integration period. And what you see is that the variable resolution mesh does a very good job of capturing the banded structure of Hurricane Sandy, as well as capturing the track associated with the storm. So the variable resolution simulation was produced with approximately 1/7 the cost of the uniform model. And it's a very good chance that at least NOAA's next generation global weather modeling system will possess this mesh refinement option and allow us in order to look at specifically, for instance, on hurricane basins in order to better capture extreme weather events in those regions. One other study that we're pursuing at UC Davis is kind of on an S2S timescale, and that's how well can we capture the teleconnections or large-scale meteorological patterns that drive local meteorological features. So one feature that we're looking at here is the so-called San Francisco Delta Breeze, a event that basically brings cooling and ventilation to the Central Valley frequently over the summer season. As heat waves are expected to increase under climate change, we anticipate that these Delta Breeze features are going to become important in order to bring relief to the Central Valley. However, there's no clear indication on how exactly these events will change under climate change. So we're using variable resolution modeling in order to basically capture the fine-scale meteorological features and then identify the large-scale meteorological patterns that are driving those fine-scale features. And so what we've been able to pick out a couple patterns in the large-scale meteorological field that are then indicative of the occurrence of a Delta Breeze event, and have used those in order to project how Delta Breeze events are going to change over the next century. One final application that I want to talk about that we're investigating is the usage of adaptive mesh refinement. This is in conjunction with Lawrence Berkeley National Lab, and that's actually adjusting the global mesh in order to add resolution for tracking individual features. For instance, tracking of a tropical cyclone. Here we're showing a sensitivity study where we've assessed basically steep gradients and high vorticity in the simulation and used that in order to place higher resolution patches as needed. So in summary, variable resolution is an emerging technology that will complement dynamical downscaling, and I believe it'll be very useful for subseasonal-to-seasonal projections. It'll allow us to create more ensemble members in order to constrain uncertainty associated with S2S projection and allow us to place computational resources where we need them in order to basically limit overall computational costs. All right. That's it for me for today, so thank you very much for listening.
Thank you, Paul. That was a very nice presentation. We'll take a couple moments here to see if there's any questions from folks. You can type them in the chat and raise your hand. Looks like we've got one from Simon here. He wanted to know, Paul, could you comment on the pros and cons we currently face if one is to compare downscaling approach with the VR approach for short-term prediction? And then he has, say if stakeholders are to choose either one for the next 5-year plan, what should they consider?
A very good question. One thing worth noting is that I think that there's an increasing push in order to move to these variable resolution systems. I think it's acknowledged. So WRF, for instance, which is used very commonly in order to do weather forecasting, that team has effectively transitioned to work on the method for prediction across scales of the MPAS model, which is an example of a variable resolution framework. So the thing worth noting, I guess, in terms of computational cost is that there's actually very little added cost associated with simulating the remainder of the globe at fairly coarse resolution, because the majority of degrees of freedom are still placed within the high resolution patch. So I would say, even though it's an emerging technology, there has been a significant amount of scientific validation on the technology in order to suggest that it is probably our way forward. And perhaps, I mean, for a 5-year plan, it's unclear whether or not it should be a targeted technology. But I suspect that at least after, on the 5 to 10-year time scale, I suspect that forecasting centers should be moving towards variable resolution in lieu of regional climate modeling or regional modeling systems.
Great, thank you. I don't see any other questions at this time. We can Q&A others up at the end if necessary. And let's go ahead. Thank you, Paul. We'll go ahead and let Ruby go next.
Okay, thank you very much. Thank you for the opportunity to present here. So, and also thank you, Chris and Paul, for giving a lot of very nice background about climate modeling and the need for S2S predictions. So in this presentation, I'm going to talk a little bit about S2S prediction, a little bit about the past lessons, but a bit more on the future prospects, particularly related to the use of convection-permitting models. And so this is work done by myself with my former postdoc, who is currently at Ocean University of China. So as Chris mentioned, previously there was an effort called MRED. It's called Multi-RCM Ensemble Downscaling. So recognizing the fact that ENSO provides quite a lot pretty good predictability for cold season climate in North America, and also recognizing that global seasonal forecasts have pretty useful skills in terms of predicting the large-scale circulation anomalies associated with ENSO. So MRED went on and used 7 different regional climate models to see whether dynamically downscaling the CFS forecast for the cold season may help us provide better regional prediction for the cold season precipitation and temperature. So just very quickly give you one result that we published back in 2012. So we look at all 7 regional climate model, and so the top figure here shows the multi-model ensemble after downscaling with the 7 regional model, and the bottom figure shows the CFS forecast And what I'm showing essentially is the correlation between the forecast with observation. So the higher the value, the better the scale. And so the left panel is a 1-month forecast, and then the right-hand panel is a 4-month forecast into the future. And you can see that using dynamical downscaling, indeed, we see some improvement in scale in terms of improving the correlation between the forecast and the observation. But the improvements are not so significant. For example, for 1-month forecast, we obviously see some improvement over the Northern Rocky Mountain and a little bit over the Intermountain West or the Pacific Northwest region. And then for the 4-month forecast, we see some improvement again in the Northern Rocky Mountain or the Northern Great Plains area. But overall, when you compare the global model with the regional downscale simulation, the improvements are not too significant, and they are perhaps more associated with some regional features such as mountains and things like that, suggesting that the forecasting scale is still very much dominated by the large-scale circulation feature that are provided by the CFS model. So then my main question is, what about the summer season, right? So if you look at the summer season, potentially there might be another predictability coming not only from the large-scale circulation associated with ENSO events, but potentially some local processes such as like surface soil moisture could potentially be important. And so this is a study that we published back in 2015 in GLL, in GLL, where we use observation data and then look at what might provide predictability to the summer precipitation over the continental U.S. And so in this figure here, we are looking at the soil moisture in this gray box, and then correlating that with the precipitation in June continentally. And we see pretty good correlation in an area kind of like in the Northern Rocky Mountain and the Northern Great Plains area, suggesting that soil moisture in the springtime can provide some predictability for precipitation in the summertime. On the other hand, if you look at the ENSO index, which is related to the sea surface temperature, we see not so much predictability provided by ENSO for the summer precipitation. And the reason why soil moisture in springtime can provide predictability for precipitation is pretty clear when we look at the partial correlation, now looking at the soil moisture together with the evapotranspiration. So we see that spring soil moisture has an important effect on evapotranspiration in the summer, which then of course provides some of the moisture sources for precipitation and therefore potentially providing an important influence on precipitation in the summertime. So then we can see that potentially not only the large-scale circulation but the local processes such as soil moisture could be important. So then I kind of like think about what might a regional model or downscaling, dynamical downscaling might provide us in the cold season versus the warm season. So if you think about dynamical downscaling, typically we get large-scale circulation anomaly coming from a global model such as CFS, and then you have a regional model that can represent, so take the large-scale circulation as boundary condition, and then you have better resolved regional forcing such as topography, like mountain valleys and things like that, and that together define the regional response in terms of precipitation and temperature. And so in the example that I show you for the MRED project, we found that the large-scale circulation has a major control over the regional response, even though the regional forcing such as topography also has some effects, but the effects appear to be not so large, though it does provide an opportunity for regional model to improve upon the regional response. For the warm season, again, we have large-scale circulation anomaly that could, again, be provided by a model such as CFS. But now the regional model provide a better resolved regional forcing such as mountains, but it also provide regional surface anomalies such as soil moisture, which are influenced by the large-scale circulation. So what I'm emphasizing here is the interaction between the regional response, such as precipitation, with the regional surface anomalies, such as soil moisture. So together, this predictability coming from the soil moisture influencing precipitation, which at the same time might provide changes to the soil moisture and co-evolve in a sense. That might really be a critical part about using a regional model that might improve upon the global model in terms of providing S2S forecast at the regional scale, is because of not only the regional forcing, but also because of the importance of soil moisture that could evolve with precipitation. So to test out these ideas, I'm going to show you some results coming from regional climate simulations, although we can also do this type of experiments using a modeling system such as the one that Paul talked about, the global variable resolution model. One of the biggest challenge we have in providing S2S forecast for summer season is really convection, right? I mean, we know that most climate models don't really produce convection very well, particularly for a kind of convection that is associated with something called mesoscale convective systems. So these mesoscale convective systems are quite ubiquitous, and they occur a lot on the east downwind side of the mountains, and so the central U.S. definitely is very much affected by mesoscale convective systems. And they typically account for about 64% of the warm season precipitation. And so just as an advertisement, we about 3 weeks ago, we published a paper in Nature Communications where we looked at historical data, use an MCS tracking method to really identify what might have caused changes in mean and extreme precipitation in the past, and we found that actually the increase in both the mean and the extreme precipitation in the past have been mainly associated with MCS that have been getting more intense and also lasting longer in the last 35 years. And so it speaks to the importance of really being able to simulate this kind of systems. And another study suggests that the warm biases that we often find in climate model over the central U.S. is in fact related to the fact that climate models cannot produce these kind of mesoscale convective systems, and so the models are too dry, and therefore the temperature is too warm. Again, speaking to the importance of being able to simulate this kind of systems in climate models. And so we have performed several set of simulations, pretty much using the Wolf model covering the whole continental United States. And we apply our MCS tracking method to look at MCS statistics simulated by the model at 4-kilometer resolution, where we did not use a convection scheme and instead allow the model to explicitly resolve convection. And so this figure here shows a comparison of the observed and the Wolf model simulated MCS frequency versus the lifetime, how long an MCS lasts, which is really important. As I said before, we find that MCS has been lasting longer over the last 35 years. And so we see that the model quite reasonably captures the MCS frequency as a function of MCS lifetime. And we also compare MCS frequency versus event rainfall, how much each MCS produce rainfall. And so this is, again, a pretty good statistics comparing observation with simulation. And so now we particularly look at the diurnal cycle of precipitation produced by the models. We know that most climate models have a lot of problems in simulating the MCS and therefore the nocturnal timing of precipitation. And so here I compare 6 different simulations. In the first 3 simulations shown in red, we used the Cambridge parameterization at 2 resolutions, 36 kilometers, 12 kilometers, and then at 4 kilometers we turn off convective scheme. And then in another set of simulations, we use a so-called scale-aware convection scheme. This is called the Grell-Frieder scheme. Apply that at all 3 resolutions. Even at 4-kilometer resolution, we allow the GF scheme to be applied. And we see that with the Cambridge scheme, quite typical results showing that most precipitation falls during late afternoon hours. As soon as we turn off convection scheme, we see this dashed red line here without any convection scheme using the model as a convection permitting model. it now captures the nocturnal timing, kind of the early morning maximum. But also interestingly, with the ground fighter scheme, which is a scale-aware parameterization, even at 36 and 12 kilometer resolution, the model was able to capture this timing, nocturnal timing of precipitation, suggesting that this could potentially be a useful approach to look into the future at this sort of resolution where it might be feasible to do even with, for example, a global variable resolution model. So now, again, looking at our model simulations, using the MCS tracking method, we can track the infrared temperature, we can track reflectivity in the model, and then track all the precipitation produced by the models. And what we found is that in the central United States, basically there are two different precipitation regimes. One is associated with isolated storms that typically maximize around late afternoon, kind of like 4 to 6 p.m., and then another type of precipitation that is associated with MCS that actually produce precipitation mostly in the early morning hours. And the observation and the comparison with the model show that the model at 4 kilometer resolution in this particular case is able to capture both the isolated type of storms as well as the larger organized type of storm, which is called the mesoscale convective systems. So now the question is, so what? I mean, what is important about being able to simulate the two types of storms together? And I'm going to show you this is actually pretty important. So here I look at the land-atmosphere interactions simulated in by two models. One is at 12 kilometer resolution using the Cambridge scheme, and then another one is without any convection scheme using the model as a convection-permitting model, CPM. And now I divide the model simulations for each day into a so-called wet regime versus a dry regime by the fact that if in each day, if the soil moisture is 1 standard deviation above the long-term average, I call it a wet regime. And if it is 1 standard deviation below the long-term average in terms of soil moisture, I call it a dry regime. So in the 12 kilometer simulation using the Cambridge scheme, we see that precipitation, which is shown by the blue curve, pretty much track the growth of the boundary layer, which is shown by the green curve. Essentially during the day, as the boundary layer grows, then the model produces peak precipitation during around like 4 to 6 p.m. It doesn't matter whether it is wet regime or dry regime, the model just is completely locked to the phase locked to the growth of the PBL. But in a 4 kilometer simulation using convection permitting model, we see differences in the wet regime versus the dry regime. In the dry regime, it's not too different from the 12 kilometer simulation. So precipitation is phase locked to the growth of the boundary layer, suggesting that rain does fall in the afternoon over dry areas. But in a wet regime, actually this is the regime where you would see the mesoscale convective systems with the precipitation peaking at midnight, which is completely decoupled from the growth of the boundary layer. And so with this type of model, you are able to distinguish the two types of precipitation system, isolated precipitation associated with afternoon precipitation over dry area versus wet area where the precipitation is mostly associated with mesoscale convective systems in the nocturnal timing with nothing to do with land-atmosphere interactions. And so I'd like to summarize what I have just told you. I think the important point is that soil moisture is an important source of predictability for summer precipitation in the central United States. So unlike the wintertime, which is where the predictability may be mostly coming from ENSO or sometimes MJO, for summertime soil moisture is important. And I show you that convection permitting models can simulate realistic characteristics of MCS, which a lot of climate models at coarser resolution relying on convective parameterization are not able to do. And therefore, they are able to capture the diurnal timing of rainfall. And with CPM, the model able to simulate the rainfall associated with both isolated storms. These are smaller storms typically occur in the afternoon hours versus much larger organized convective storms that peak at midnight. And these two basically play a different role in terms of how land surface processes might be important in the development of the storms. So I suggest that using CPMs may be like promising tools for improving S2S prediction because of the fact that it would be able to simulate the two types of systems with different land-atmosphere interactions and the importance of soil moisture and then harnessing this predictability coming from the soil moisture. And I also want to make an additional point that I show you some results of the WOLF simulations using the Graph-Writer scheme, which is supposed to be a scale-aware parameterization. And it does seem to produce much less sensitivity to model resolution. So potentially a big challenge in variable resolution global model for summertime application is that you do need to have a connection scheme that is scale-aware so that you can apply it to the coarse resolution area as well as the high resolution patch that Paul Ullrich talked about. So I think being able to investigate further that type of scale-aware parameterizations would be really important going forward with application of a global variable resolution model for summertime predictions. So that's all I have. Thank you very much for listening.
Thank you, Ruby, and a very nice presentation as well. And we'll take a couple questions here if they come in. Feel free to raise your hand or type them in the chat feature. We do have one here from Mike Patterson. Ruby, he wants to know, do you suspect similar results in the transition seasons, spring and fall, as for summer?
Yes, spring definitely. We have actually performed simulations also for spring between April, May, and June, and we see similar results. As a matter of fact, in the central U.S., mesoscale convective systems start to occur a lot, actually even in springtime. And so the ability to simulate the springtime MCS using this kind of CPM is really important. And also back to the paper that I talked about that we published a few weeks ago in Nature Communications, we see changes in the MCS in the last 35 years, both in the springtime as well as the summer season, showing this increasing longer lasting and more intense MCS over the last 35 years. And the paper explained why that was the case. Yeah.
Great. Another question. If there was an MRED 2, what would be your assessment on the influence between CPM and land model on S2S predictability for the warm season?
Yeah, well, I would really look forward to have an opportunity to do something like an MRED 2. I mean, in MRED 1, I mean, we only look at cold season prediction because of the fact that we felt that at that time, I mean, we weren't able to use even like a regional model at this kind of 4-kilometer resolution, and we know how bad climate models could be in producing convection and MCS and stuff like that in the warm season. So we didn't really try to do an experiment like that. But with the availability of the CFS reforecast for the summer season, I think it would be really important for us to test out this kind of capability to see how much a CPM can help improve over the scale of a CFS because of this ability to simulate not only MCS but also the interactions between, the land atmosphere interactions that should play a very important role in the coevolution between soil moisture and precipitation. So I think there is a lot of potential for that.
Great. Thanks, Ruby. I'm going to relay a comment that Chris sent into the chat to everyone if they didn't see it, and then we'll move on to Emily. So Chris wanted to make the point that it is important also to say that land surface processes encompass both soil moisture and vegetation, can potentially now incorporate dynamic vegetation.
Yeah, and that is a very good point. Certainly land surface processes involve quite a few other factors too. And over here, we only look at soil moisture, but other factors such as vegetation would be important. And there are interactions between vegetation with soil moisture and other land surface component as well. Yeah, very good point.
Great. Thank you very much, Ruby. And we'll go on to our fourth presenter. Emily, are you with us?
I am. Can you hear me?
Can. Sounds great. Take it away.
Okay. Good. Thanks. So we've been here for about an hour or so. If you all want to take a seventh inning stretch, you can stand up and reach for the stars or something. Wake up a little bit. And we've had a couple of really interesting talks that zoomed in on things looking for higher resolution. And I'm going to go sort of in the opposite direction and zoom out and look at some large area aggregates and see what we can see. This is the prediction of short-term climate extremes, generally using data from the North American multi-model Ensemble, is sort of a project I've been working on off and on for a couple of years. Huub van den Dul refers to it as my hobby, which I actually find a little bit depressing. One would hope that was something like sailing or reading, but apparently this is my hobby. So we've had some good coverage on why early warning systems are desirable. So I could show again what Chris showed, that chart from the NAS, and I think that hopefully we can all just accept that these are desirable for many reasons. And at an operational center, where I am at the Climate Prediction Center, we do have a lot of interest in these early warning systems for extreme events. And so what I tend to look at here is what can we do with what we have? And what we have being global climate model systems like the North American Multi-Model Ensemble, the NMME. What I'm showing right here is not a forecast for an extreme. It's just the forecast from October made for November. And over the last 5 years of operations of the NMME, where the monthly mean system went live just over 5 years ago. And so we've had continuous forecasts once a month for over 60 months now. And what I've noticed is that while the skill for precipitation forecast in general is quite low, at the shorter lead of a 1 month lead for the following month, so not a seasonal, but you could think of it as more of a 4 to 8 week forecast, there's some skill at this level, and so it intrigued me to look a little bit further into what we could get out of what we have. And this shows, let me find my green arrow here. So this is the observation here. We had an extremely dry November in the southeast, which spawned a lot of forest fires and such. And in fact, at a 1 month lead, the NMME did have a dry signal over here, and we actually had a rather good area average anomaly correlation for that month. So it was just a little bit more impetus to look into these. This is the somewhat older work that Huub van den Dul and I did looking into the overall prediction skill for extremes, and we looked at surface temperature and precipitation over North and South America. These are just a couple of example figures, but this is the threshold essentially at which you are defining an extreme. So moving to the right, you're getting more and more, your sample is confined to more and more extreme events. And you actually do see an increase in the anomaly correlation from these forecasts as you get to a more and more extreme sample, implying that the skill is actually better than forecasts for all what I'm calling all events, which is the every event in the record. And this is work from the CFS. So, sorry, clicking here. Okay. And then this looks into just seasonal temperature extremes, a little bit more proof of concept here. This is using the NMME. And each dot here, this is the, on the x-axis you have the anomaly correlation for all forecasts. And then this is just for negative extremes on the left here, and then for positive extremes on this right graph here. This is for Northern Hemisphere area averaged, area aggregated temperature result. So this is 1 square for each model, and each season, this is a seasonal temperature extreme. And then the black boxes show the NMME. And in fact, you do see this, this forecast skill in terms of the anomaly correlation is still higher for the extremes than for the than for the all forecast aggregates. And then as you get to higher skill forecasts, this relationship is actually stronger. So areas where you have better skill in all, for all forecasts, you tend to have even better skill for the extremes. So I wanted to just cover briefly existing real-time forecasts for extremes. There are not very many of them, and there may be more than I'm aware of. It's a little hard to just Google for operational forecasts for extremes. But this is a nice map that's put out by the IRI, and they've been doing this for several years. They do just the lead one forecast. So this is the November forecast for DJF precipitation, and they do a highly enhanced, and slightly enhanced categories for both above and below normal precipitation. And this is their, so you unsurprisingly see much better coverage for temperature, which generally has a lot higher skill. But there was an assessment done of these forecasts by Tony Barnston and Simon Mason back in 2011, and they found that these forecasts for extremes were issued relatively rarely, and much less often than they actually occurred. And the forecasts here are a product of both model output and statistical model output, and also the forecaster's judgment. So there is a subjective component in this, as there is in all of our official forecasts at the CPC. However, they did find when these forecasts were issued, the reliability and the calibration were, quote, generally satisfactory. But forecasts for heavy precipitation were overconfident. So the probabilities were stronger than they were justified to be. This is a CPC product, which we've been issuing for a little while now, not terribly long. This is just for week 2 is what I've highlighted here. We still have a days 3 through 7, which is really a weather forecast product. But we do have some hazards forecast for the days 8 to 14, which is week 2, so getting into the subseasonal range. And this has actually quite a lot of categories that are possible here. What I'm highlighting right here is the probabilistic forecast for temperature extremes. So in fact, we do have some higher probabilities for extreme cold in week 2 coming up here. So get out your winter clothes. Looking into the skill of NMME precip extremes, this is just a little recent study I've done using the NMME. I looked at the so this is just some details about the NMME. As I said, we've been live for 5 years. There are always between 6 and 8 models in the real-time suite. We have had, I believe, 12 participating models so far. Some of them have retired. And there's a common hindcast period of 1982 to 2010, which is used for calibration and for retrospective analyses. My definition of extremes here, it's varied a little bit through the studies that we've done, but here is the top decile. I'm just looking at extreme wet precipitation in a single month. So this is determined by fitting a Gaussian distribution to both the observations and the forecast. And since precip tends to be a skewed distribution, we first transform all the values by raising them to the quarter power, which is a little bit of a rough technique and in certain does not adequately Gaussianize the distributions at every single grid point, but in fact we've done a couple of assessments to find and found that this is reasonably satisfactory, and this transformation does capture the overwhelming majority of extreme events. So we use a threshold of the standard deviation to find the 10th percentile. And looking at the global land average, since precip skill tends to be low, aggregating as many grid points as possible increases the statistical significance. So the heavy lines here are for the NOAA multi-model ensemble. This is the ensemble, the multi-model ensemble mean of all 8 models that I have used in this study. These are the currently available in the forecast suite models. So it includes the CFS version 2, 2 Canadian models, CAN-CM3 and CAN-CM4, as well as GS5 from NASA, CCSM and CESM from NCAR, and 2 GFDL models, the CM2.1 and the FLOR. So these heavy models are, heavy lines, are the multi-model ensemble, and this is for just the upper tercile, so what we call above normal when we make operational forecasts, and then this is for just the upper decile. Of course, these events are included in this forecast here, so it's not completely exclusive. And then the thinner lines are for the individual models. And you can see that this effect of higher skill, higher anomaly correlation for the extreme events is consistent and has a much stronger effect when you are looking at the multi-model ensemble, which has a higher score for almost every situation. There are a couple of times when a single model does exceed the multi-model ensemble. And then these are for each of the target months. The seasonal cycle is obscured by the fact that this is global, including north and south, northern and southern hemispheres. If you decide to look at a contingency table to see more of a hit rate and false alarm rate way of looking at this, which is ultimately the way that our forecasts our operational forecasts are assessed. You find again that this is the skill score here, and you find that the skill score for the upper decile, while the hit rate is in fact lower, which is unsurprising, this is a smaller forecast subset, your skill score is in fact higher again. Another piece of interest here is the forecast bias. We find that overall these events are forecast only slightly less often than they occur. So from an objective system, which this is using only model output, we don't have quite the same bias issue as forecasts that involve a subjective component. A map here to show us what kind of areas we can see any improvement in and any skill at all in the forecast for the 90th percentile. And you see some of the areas you would expect that have a strong ENSO signal. This is all 12 initial conditions aggregated. So again, the seasonal cycle is obscured, but you also do see some coverage in areas that aren't necessarily strongly influenced by ENSO. So getting from here to there, actually developing a useful outlook from this work or from really any kind of model output is challenging and requires some creativity. What I've looked at are just deterministic forecasts, the forecast for a specific anomaly, but real-time outlooks will be probabilistic, and that raises a bunch of questions: which thresholds to use and how do you do calibration? And then an issue that has come up recently is the changing likelihood of events between the hindcast and the real-time period. Just for example, over the last 4 years, so 2012 through 2016, over 60% of events have been in the above normal tercile. So you would hopefully expect more like 33% of events to show up in that tercile, which with global warming is not a surprise, but it does raise a problem for a forecast that's based on thresholds determined from a hindcast. And then, of course, precipitation is special, and we may require some creativity here too, including possibly a regional index forecast, and then high and lows will need different treatment. There are also possibilities like looking at the characteristics of a seasonal forecast, the number of extreme events, consider forecast. This is just preliminary work in and getting to an actual probabilistic extreme outlook on a seasonal timescale will take a little bit more development for sure. All right, and that's ending on a very extreme.
Thanks, Emily. Nice presentation. So we're definitely getting close to time, so we'll take about one question if we have one. And we can always queue those up for the end too. So let me see if anything comes in. Great. We have one question here. If increasing resolution can increase the skill of NME on the convective type of systems, would it be practical for CPC to adopt such an approach? Is there hope for a CPC-SPC cooperation? And he means SPC as in Storm Prediction Center.
Right. Well, there currently is a line of communication open between the SPC and the CPC. I'm not an actual forecaster, so I don't know quite the details on that, but I do know that the hazard product is in fact developed in communication with the SPC.
Great. Thank you, Emily. And thanks for the questions, folks. We're going to go on here to our final presentation by Mr. Trent Ford. Trent, are you with us?
Yep. Can you hear me?
We can. Thank you.
All right. So I'll wrap this up and I'll keep us within time, I promise. So now that Emily zoomed us out to all these extremes, I'm going to zoom us back into just extreme heat. So the article we wrote was focused on S2S forecasting of extreme heat in the U.S. and the role of land atmosphere interactions in that. I just want to acknowledge my co-authors here, Paul Dermeyer and his student David Benson at GMU. All right, so extreme heat, I don't think I need to describe the threat that extreme heat poses, major implication for human health. And of course we get the enhanced vulnerability in urban regions as well with the UHI effect. As the map on the right-hand side here shows the report from NOAA in 2012, we've seen a realized as well as a projected future increase in heat wave intensity, duration, and frequency with some regional variability, but generally across CONUS. There aren't many places where heat waves and extreme heat aren't projected to increase in all three of those categories. Now, extreme heat, typically defined by maximum temperature, often precedes, coincides with prolonged dry, rain-free periods, a drought often. And that's really where we want to explore the connection between the land surface and the atmosphere. And I'll describe in a little bit that connection between the desiccation of the soil and then the subsequent modification of temperatures for the onset of that heat wave is really what we're focused on. And unlike the drought that may initiate the extreme temperature event, these heat waves are more short-lived. So we may, using some human heat stress indices, may only have a 2 to 3 day period of extreme, what could be defined as extreme heat, and that can be manifested on even shorter than subseasonal timescales, depending on what sort of atmospheric features can establish. But the S2S timescale is really ideal for trying to determine the capability of these models to forecast these extreme events. And so since my co-author Paul isn't here, I think I'll hijack the talk and talk more about soil moisture than anybody would care for. So the land atmosphere interactions were really digging down into soil moisture, pun intended. So the land surface has an inertia or memory, as it's called often, and Ruby talked about this a little bit as it forms to convective precipitation. But for temperature, definitely it is an important source of atmospheric predictability on S2S timescales, and really when it comes to the linkages between the soil moisture and temperature, it comes down to the constraints of latent and sensible heat. So if we get a prolonged period of either a rain-free period or just a drier than normal period, we can get drying out of the soils, and that moisture deficit is conducive to sensible heat transfer over latent heat, and we can get an increase in the air temperature. The figure on the right-hand side here is just an interesting figure from a study in GRL where we saw that the response of monthly percent hot days, just percent of days over the 90th percentile for that month, and its response to soil moisture anomalies of the previous month, that response was asymmetrical. So we saw that the right warm extreme tail, that maximum temperature distribution, responded more strongly to the drying out of the soil the previous month than did the median or the cooler tail. So what that suggests is that as we see more continental drying or maybe perhaps more drying out of those soils during the warm season in a place like the central U.S. and the Great Plains, we could see perhaps more of those extreme events and a shift towards more frequent extreme heat waves. And just as we're seeing projections of future projections of increased heat wave incidents, we also see that the degree of land atmosphere coupling in North America is also projected to increase, both in aerial coverage and in seasonal duration. And to make that point, this is a figure that Paul published in 2013 in a paper. The top panels here just showing the seasonal multi-model mean of the terrestrial coupling index, which is a physically based index that measures the coupling between the land surface and the atmosphere, from the CMIT-5 models, and then the bottom showing the sign degree of the consensus among the models for the RCP 8.5 projections. And what we can see is that the terrestrial coupling index is projected to both increase in intensity, so the strength of the coupling between the land surface and the atmosphere, and the spatial duration, or excuse me, spatial extent. So that's just to say that the linkage between the land surface and the atmosphere, that partitioning by the soil and the vegetation, the partitioning of latent and sensible heat to influence the temperature, that's projected to become a more significant portion of temperature variability. So our positive land atmosphere feedbacks can prolong these dry anomalies. We get atmospheric circulation patterns that can establish to dry out the soil, rain-free periods with high evaporative demand, and those dry normal soils can then create that positive feedback to intensify and prolong those warmer than normal conditions, even beyond the point after which the atmospheric circulation that initially forced it is dissipated. And that is that land surface memory that I spoke about. And the way that we want to define that, or the way it can be defined, that land surface memory, is through the forecast skill improvement. So to compare different models with different land surface initializations, and to see how a more realistic land surface initialization helps improve or doesn't help improve the skill as far as heat wave forecasting. As a figure from Randy Foster's paper in 2011 shows, in this particular case, the magnitude of the initial soil moisture anomaly, which related directly to the realism of that initialized soil moisture anomaly, directly influenced positively influenced the S2S forecast of temperature. And so it suggests to us that as we get more extreme soil moisture initializations that get more towards realistic conditions of very dry or very wet soils, we see a positive bump in the skill of the S2S temperature forecast. And so in this particular case, using a multi-model ensemble really is advantageous for trying to fingerprint the influence or the importance of realistic land surface initialization, and really talking about soil moisture in this case. So both the NMME and the S2S prediction project provide this unique opportunity to be able to really, like I said, fingerprint the importance of soil moisture initialization and realistic land surface initialization for these S2S forecasts. Like I said, I squeezed in some of my soil moisture propaganda here. One of the biggest issues with even beginning to try to quantify the importance of the realistic initialization of those initial conditions is observing the land surface. So just figuring out what the land surface state is, what the soil moisture state is, before we try to assimilate that into the model. And that all starts with high quality observation networks. And no matter if it's temperature, precipitation, or in this case soil moisture, those high-quality observations are invaluable for forecasting any extreme, let alone extreme heat. And so there's been this recent advent in soil moisture information. I thought that was important for the article and this presentation to describe, and that comes alongside with the International Soil Moisture Network in the Netherlands, the North American Soil Moisture Database here in the United States, from which the image here is showing all of these assimilated in situ observations of soil moisture. And then those can be augmented by the recent advances in remote sensing soil moisture, both in the SMOS and the SMAP missions. And those are very, very important to be able to capture the spatial variability of soil moisture as well that you can't get with these in situ stations. And then, of course, there's the NLDAS2, the North American Land Data Assimilation System, which can provide those gridded soil moisture fields down to the root zone, which is often missed by the remote sensing data sets. So even with this boom in soil moisture information, there's still a lot of challenges that remain in just trying to observe the soil moisture state across CONUS, for example. One of the biggest ones that I'm struggling with is integrating all of these diverse sources of soil moisture information. So you have the spatial mismatch between the model, the satellite product, and the in situ sources. And the in situ sources are still, of course, the benchmark, but trying to how to use them to validate is still a challenge. And then how to assimilate that into S2S forecast, for example. And then a big one that is kind of glossed over in the modeling world is establishing a science and industry standard of in situ soil moisture monitoring. So we want to use these stations to validate the products that we put into the initial conditions for the model. However, these in situ stations are run by disparate sources that, unlike national temperature precipitation monitoring networks, they all have their different standards for, or maybe don't have any standards at all for deploying, implementing, calibrating the in situ soil moisture sensors. And I would argue even more than temperature and precipitation, having that industry standard is very important, because not only with soil moisture, not only do you have the atmospheric variability, but also the variability of soil texture and vegetation types that sensors are deployed under. So that's still something that is a challenge when you're trying to put all these sources of information together. So Paul and I are working on a project to evaluate numerical forecast models' ability to predict heat waves on S2S timescales following droughts in the United States. And then, of course, relating this to relating the model forecast performance to land surface parameterization and initialization. And so what I'm showing here are just some recent results, some correlations between the standardized precipitation index, which is similar to what Emily was talking about with her precipitation extremes, so just a meteorological drought index, and correlating that with evaporative fraction, vapor pressure slope, and the LCL to try to at least try to estimate in some way the linkage between summer moisture availability or drought conditions and boundary layer conditions. And although we see pretty strong correlations throughout most of CONUS, particularly in the Great Plains and throughout the Southwest, between vapor pressure slope and the evaporative fraction, we see that the evaporative fraction correlations are generally stronger, and suggest that linkage between antecedent drought conditions and the onset of heat waves in the boundary layers, just that those surface fluxes are really the main linkage. So how the soil moisture anomalies are affecting those surface fluxes are really what's connecting those two together. At this time, though, it's important to put that caveat that there's no cause and effect that can be determined from this analysis. And some more recent, very hot off the press results here. Just comparing MERA2 with the CFS2 model, we're showing the rank probability score and relative entropy here over CONUS at a 1, 3, 5 day lead. And what we're seeing is that for heat wave forecasting, there is some skill beyond a climatological forecast at a 1 day and less or so a 3 day lead, particularly in the Pacific Northwest or the northern part of the Intermountain West. But for both rank probability skill score and the relative entropy, we see a decay of skill, really no skill across CONUS beyond that 5-day lead. And the same thing we see with relative entropy as well. So this is just kind of a first cut at some preliminary evaluation of the model as far as being able to forecast those extreme heat. And what we're seeing is really a drop-off in skill beyond a 1 to 3 day lead. And of course, these results that I'm showing here are with a 4-category probabilistic forecast outcome, where we have 1 no heat wave category and 3 different intensities of heat waves. When we remove the no heat wave category, almost all the skill disappears even at the 1-day lead. So most of the skill that I'm seeing here is the fact that the model is picking up that most days there's not a heat wave. So there's lots of challenges and recommendations. Unfortunately, I have more of these than I do awesome results, but that's just the stage of the project right now. So there remain large knowledge gaps concerning the influence of model land surface initialization on heat wave forecast reliability. That's the kind of what we're trying to get at right now, what the importance of a realistic land surface is for forecasting those heat waves. But it is still important to emphasize that the land surface source of memory is important, particularly when we're trying to connect or simulate that connection between the land surface and the atmosphere, because we do see the connections between soil moisture states and subsequent extreme heat. And of course, the continued improvements to precipitation, soil moisture monitoring and modeling infrastructure is expected as we get more soil moisture, better soil moisture information, better precipitation information. That's expected to help better these S2S climate forecasts. So with that, I thank you, and I'll take questions.
Great. Thanks for keeping us engaged, Trent, through the presentation. We'll take any questions here for a couple minutes before we wrap up. We have a question from Simon towards precipitation. Could you comment on soil moisture feedback on flood risk? Given that saturated soils release runoff more rapidly, thereby enhancing flood risk, how could CPM enhanced predictability take advantage of soil moisture's inherited S2S predictability?
That's a really good question. Yeah, the flood risk is even more challenging because of the short timescales on which we need soil moisture information. But yeah, I think that like you said, the inherent S2S predictability in soil moisture and the improvement in these gridded soil moisture products could also benefit flood forecasting as well. And what Ruby was talking about with the CPM, that is definitely something that is a good outlet for improved land surface information.
Great, thank you.